Okay, this is Application Layer, Chapter 2, Part 2. In the first part of this lecture series, we discussed how there is an independence relationship between the application and transport layers in the OSI and Internet models. We also talked about why that was important. In this part of the lecture series, we're going to look at several different application protocols and how they look communicating on the network. Applications have their own protocols that govern the types of messages and syntax and semantics and rules for how the messages get sent on the network. This is absolutely critical. Computers, let's be frank, are stupid. They lack the ability to determine the context of a message. They can't handle any ambiguity in the message. If you have any kind of vagaries, the protocol just won't work. Application developers need to design the messages that are exchanged carefully and thoughtfully. Each application will have its own set of messages, and for example, if we were to build a web-based email service, we would need messages that allow users to request an email message and the server to return the requested message. But we'd also need to have messages that represent errors, such as the requested message doesn't exist. Every type of action between a client and a server is going to need to have some kind of message that can be exchanged to handle them. Each of those messages needs to be clear and concise. It's important that the syntax is clear and completely unambiguous. If the receiver of the message can't understand the message because it's not well formed, it needs to be able to issue an error message in response. For example, this first message, give me 32, has syntax that kind of lacks clarity. Like, it's a little contrived, I admit, but we don't really know exactly what this is referring to. The second form of this, maybe we're going to ask the email server to send us message number 32. That's better. Like, it's a little bit more clear. We could look at this and see, well, if I see the word send, I can continue parsing the rest of the string. If I see this ID, look for the equals and then read the number out of there. Like, I can get the individual pieces out of this at least. Arguably, the third message is even better syntax. It's just 4 integers. And we could presume, for instance, that command number 25 is going to be a retrieval command, maybe. 01 means we're going to be asking for an email message type. This 01 might mean that we're going to be asking for the ID number as opposed to some other field of the message. And then the number is going to be whatever matches that ID field. So if I were to design my protocol to work with these 4 integers, that actually might be even more clear and more easy to understand if this is a valid message or an invalid message. It's also equally important to have very clear semantics about the different parts of the message. In this first form, while this is pretty close to how we might speak, it's very context dependent. And the second form is definitely better, but it might be a little harder to pick out the individual things reliably, and so we may have trouble getting the semantics of the message as a result. And again, we go back to this version is pretty straightforward. But again, if you're the application developer, you have some control over this. In some cases, you're just going to be interacting with a predefined standard. For instance, if your job is to program to the web standard, then you're going to have to deal with the HTTP protocol, which we'll look at shortly. Unfortunately, application standards vary widely. Some applications have official, open, and well-publicized but rigid RFCs. We learned about those in Chapter 1. And those RFCs are going to govern their message formats. We'll take a look at an RFC later in this series. Good examples of some of these are going to be the web and email standards. We'll see exactly how the detail that they spell these things out. Other applications can have a more closed and proprietary format. Applications like Skype or Facebook, and I don't mean to pick on these as particularly bad. It's just that these aren't intended to be shared beyond their corporate developers. You're expected to use Skype, not program the back end of Skype. It doesn't mean that they don't have any standards either. It just means that they aren't widely published. So I'm sure somewhere in Microsoft's library they have very detailed definitions of how the Skype protocol establishes a connection and sends data and gets responses and all of that stuff. It's just that you and I can't just go to a standards body and pull them. And it shouldn't be a surprise. So imagine if one could just go and create their own Skype compatible client without having to pay the licensing fees to Microsoft. This would clearly harm Microsoft. It would take away their customer base. You could possibly be using their servers in an unintentional way. You could even be using it to analyze traffic of existing customers and be able to compromise data. I mean, all kinds of terrible things could happen. And would certainly be likely to bring down the Nazgul, or I mean, Microsoft's corporate attorneys, which, let's face it, are probably Nazgul, down onto you, and the pain would be fast and furious. So if you remember the OSI and TCP model, we aren't really concerned about what the application is going to do with the data that it's received. That's a different class. Like, that really comes down to user interface and software engineering, and kind of above us. We're really concerned with how a web page or an email gets those messages back and forth, just the transport between the application and the rest of the network. So unfortunately, we had to look at some of these application protocols to understand that, because it's going to give us a clue as to how messages get exchanged between clients and servers. So perhaps the best and our first example of an open protocol today is the Hypertext Transfer Protocol developed in the 1990s by Sir Tim Berners-Lee. Although at the time he was just a grad student and certainly not a sir. The HTTP is governed by RFCs 1945 and 2616, as well as a few others. HTTP is not the actual contents of the web page, it is just the transfer of those objects back and forth. So in the term object here could mean web page, but it could also be images, audio, video, or really anything between the web client and the web server. The protocol has assigned numbers by IANA. HTTP port 80 is used for kind of standard web traffic. HTTPS is port 443. And HTTPS is the encrypted form of the Hypertext Transport Protocol. But web servers can run on any port number. It's common to see port 8000, 8080, 8888, etc. And these are often used for testing on a local machine. So recall that ports above 1024 don't require any elevated system privileges to open up. So as a user, I could go to Clipper or any of our shared servers and run my own web server on port 8000. And if you weren't paying attention to the different port number, I kind of would inherit the authenticity of that server for my own personal server. So we had this problem back in the old days when the university had user accounts on the web server. So the same machine was our web server as was student server, and so students were running their own web servers all the time, and they would look like they're coming in at www.ship.edu like they're authentic, but they were really fake. The HTTP protocol defines several request types, and they're often called the create, replace, update, and delete, or what we call CRUD. The most common two request types that you'll see, though, are get and post. Obviously, put, delete, and patch are going to require elevated privileges, and we're not going to see a lot of that. The Create and post, on the other hand, are kind of the natural way that we work with web pages. What's really interesting is, due to the clear and unambiguous documentation, it's possible for anyone to create a client or a server that meets those requirements. So we don't all have to use Apache web server or Firefox or Chrome or whatever standard web browser. The animation that's running on this page shows a simple web request being made by a human, me, using the netcat command, or abbreviated NC. And you'll see that I'm doing nc www.ship.edu to port 80, and then I type in this magic string of get/http/1.1. I say what host I think I'm connecting to, and then I hit enter, and then it spews out the HTML. The HTML in this case is the contents of Ship's web page. I could do the same thing to other documents. So for example, I could use this to retrieve an image off of the web page and save it to a file. We could do all types of different web requests this way. A few years ago, I embedded something like this into a Perl script. And what it did is it connected to my kids' school's learning management system, and every day it would retrieve any upcoming homework assignments and any new grades that were posted. And so I got an email message every morning that basically told me where my kids were at, and so when they came home from school, we could have a conversation of what needed to be done or what went wrong in the previous. And it worked because I could just essentially open up this network connection to the school's website, log in with my credentials using a post command, and then use the get functionality to get the web pages, and then just pick out the pieces that I wanted to see. So I just want to take a look at an RFC for the World Wide Web. And so let's do a Google search for RFC 1945, and that'll take us here to the IETF. Remember, that's the Internet Engineering Task Force that kind of maintains all of these. And if I look, we end up with, oh look, there's our friend here, Tim Berners-Lee, as well as a number of other people who were working on this standard. This was the first one, HTTP 1.0. And as we roll through here, we can just kind of see all of the different features that the web protocol supports. So let's just take a look. Sometimes you'll see messages. Let's take a look at these informational messages. So if you try to do a command and you get one of these info responses, it'll tell you exactly what the error message means. So for example, 200 is okay. There's the redirection methods that tell you that the web page you're looking for is not here. Here are all the error codes. So like the 404 error that you probably have gotten on the web, that's actually part of the RFC. And so when you're looking at defining a standard, we really need to define all of the standard. And everybody needs to play by these rules to make everything work. And so this tells you stuff about what's going on in the underlying protocol. And the protocol can give you answers as to what's going on in the software and what's working or not working. Another interesting part about the RFC is it'll give you glimpses of things that maybe aren't always used, or maybe they are and you've never seen them before. So for example, if we look here at user agent, we can read about the user agent field that contains information about the web browser. So you may not have known this before, but when you connect to a web server, your browser tells the web server a lot about you. So for instance, it'll say what version of the operating system you're running, what version of the browser that you're using, what web browser are you using. And in fact, some people have been able to reverse engineer or kind of do data mining and figure out how to put identities together. So for instance, we can actually use this browser information in some cases to identify users as they move from site to site to site. Just because the exact combination of all of these different user agent strings can be fairly uniquely identifying. Things like if you wanted to implement the little pop-up boxes that come up and say enter your user ID and password to get to this web page. All of that stuff is defined in this protocol. And so there's reading through here, you can really get a good sense of how the web works, or if you wanted to do your own web browser or web client, how you would implement it, or if something's not working, why it's not working. So these protocol documents are fantastic and really good sources of information, especially at that application level. So in the last video, we looked at a packet tracer example for retrieving a web page. This trace here is using the tool Wireshark to capture live data from 2 real machines. And we can actually use this to do some interesting comparisons. Note that this used more packets than what we saw with Wireshark. And if we try to go through here and identify what's related, we can kind of, let's see if I use a pen here. I'm not on my tablet, but this connection 1 is actually part of a previous connection. And we see that it's actually trying to close the connection with the fin command. This is a TCP out of band thing. And it's requested an acknowledgement. And if I look down here, we see the same connection is closed there. This line here is actually doing the same thing, only it's being closed here on line 5. Line 3 and 4, those are opening new connections to the web server. So this web browser is trying to open up 2 simultaneous connections to the same server. So do you remember the 5 tuple endpoint? We could come in here and say that I have a TCP connection from this IP address to that IP address, port 54442 to port 80, or 54443 to port 80. Because these 2 numbers are different, it's 2 different connections. Alright, so we see that the web server has responded to, oops, this is one that we killed. Let's go ahead and mark those completely out. And those don't count. So this is all stuff that was from the previous request. Alright, so now here we see the acknowledgement to our request to open connection on this tuple. And notice that this response came before the response to number 3. So we see a little bit of out of order action happening here. Line 7 is the acknowledgement to opening the packet. So you see the server sent a synchronization command, a send command, and then it requested an acknowledgement. And so here we send the acknowledgement for number 6. Finally here at line 8 we get the acknowledgement from line 3, and we see that the server said, yep, go ahead and open and acknowledge that you got my message. And so then line 9 is acknowledging line number 8. Now the way Wireshark did this, I don't know which of the 2 connections were used. If I were live, I'd be able to click on that connection and actually see what the port numbers were. But what we can see is that the web browser sent a get/http/1.1, which is identical to what we did manually on the previous slide. Now let's see, we have line 11. Line 11 is actually the web server closing line 1, so we can actually ignore this one as well. Oh, in the end, so it sent the fin and requested an acknowledgement, and so there's the acknowledgement for that. Okay, so here's line 13. Line 13 is the web server sending data, and we can see here, or sorry, acknowledging the request. Sorry, I gotta get that right. So line 13 is acknowledging line 10. Oh boy. Line 14 is the web server sending data. So this is the response to our GET request, and we see that it responded with 561 bytes. It's actually interesting for this particular web connection that the number of bytes returned is less than the bytes that it took to request it in the first place. I'll explain why in a second. Then what we see is the acknowledgement. Now, if I had to guess, just because I see the acknowledgement here to sequence number 551, let's see, so it looks like those guys are connected. I'm going to just guess that this is using this connection, the 54443 port, not the 54442 port, just because I kind of see that's where all the action's happening. Line 16 is the web server saying, I'm done, close, and then acknowledge, and then there's our web browser closing the connection and acknowledging it. And that's it. So if we count the survivors, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we end up with the same 12 packets that we saw with Packet Tracer that were exchanged back and forth between the TCP/IP layer. I like this view better than Packet Tracer. I think mostly I'm more maybe personally familiar with it, but I think Wireshark does a nice job of dissecting the packet information and kind of giving you access to each of the different components. I like that you can kind of see very clearly who's asking for what and what's being acknowledged, and I think it helps kind of clarify things. The other thing that's really interesting is we can see that there's additional stuff that's happening. And so, for instance, if we were trying to look at the TCP keep alive, we see that's what this port 54442 is being used for. This was just for the web browser to try to keep a connection open to the web server, and it didn't need it. And so eventually, when I closed the browser tab, this went away as well. Now, I said I'd explain why the content is so small. This web page is from blank.org. It is literally a blank, empty web page. It is the minimum viable web page one can have. So it's no wonder then that the request was bigger than the response. What's also interesting is if we take a look at the times, these times are in seconds, and so some of these, like the time here, so this is tens of seconds, hundreds of seconds, thousands of seconds. This is 323 microseconds, 466 microseconds, so about 140 microseconds between these two connections being delivered out over the network. And then we see this big gap for the responses to come in, so this was about 42 milliseconds. And then after 42 milliseconds, there was just a bunch of bursts of stuff going back and forth. And then another 42 milliseconds for the results to come back, and then a final, another, was that about 30 milliseconds, 50 milliseconds of the web browser kind of figuring out, oh, this is a blank web page, and then closing the connection. So the timing information that we get from Wireshark can be really fascinating. It can also be a great diagnostic tool to try to figure out, is the delay happening on your local network, or is it happening in the transport out to the remote network? You can do Wireshark on multiple devices, so we can see, for instance, if there was a delay on the wireless network, I could look at that and see that that's where the delay is happening. So the timing data can be super useful here. Let's take a look at this video on content delivery networks, which have really transformed the way that big web servers handle traffic today. So when the web first started out, everybody kind of maintained their own little web server on their own local PCs or their nearby servers. Today, you know, we just don't do that. The world has gotten way more complex. So this gentleman will explain the ins and outs of content delivery.
Hi, I'm Ryan Sumner. I'm a Chief Network Architect with IBM Cloud, and today I'm going to help you answer what is a content delivery network. So in short, a content delivery network, or CDN, is a service that accelerates internet content delivery. So in other words, the main benefit of a CDN is that it makes your website faster. So before I get into describing to you how it accomplishes that and some of the other benefits, first I want to talk to you about some of the challenges that we have where we have users all around the world, but we don't have servers all around the world, and the experience that those users have due to that dynamic. So I've got a simple diagram here showing a server hosted down in Dallas. This is my website. And then I have users all around the world. So in Sydney, I might have 5. In London, I've got 5. New York, I might have 10. LA, I might have 10. So I've got 30 users around the world that are accessing my server and my website down in Dallas. So let's kind of follow a set of these users in their journey. Let's look at their users down in Sydney. They make a request to the website. They've got an 8,600-mile hike to Dallas and then an 8,600-mile hike back. The amount of time that takes is usually measured in milliseconds, and just that round trip might be about 170 milliseconds. For our users up in London, that might be about 100 milliseconds. Our users in New York City can probably experience about a 40 millisecond round trip time, and over in LA, about 30. So as you can see, the further you're away, the longer it takes, ultimately, the slower the website will be for you. So this is where the CDN comes into play, and this is how it actually accomplishes the increase in speed, which is by reducing the amount of distance between the user and the content, or the server providing the content. So what it does by doing that is it places these content delivery network endpoints in as many locations around the world as possible, and in our case, we're going to assume we've got one in just about every location where our users exist. So now when the user in Sydney or London or New York City or LA tries to access some content, it's first retrieved by the Content Delivery Network service and then distributed around the world. So we have a single request down to the Dallas server. It's now then distributed all around the world, and our users in London now, instead of going all the way to Dallas, they're able to retrieve that content directly from their closest geographical location, drastically reducing the amount of time that it takes to retrieve that content. So as you can see here, it's very basic how a CDN is able to provide the benefits of to the end user by reducing the amount of time that it takes to deliver the service. But what you're not seeing here is an indirect benefit, is the reduction in the amount of traffic that actually hits the Dallas server. So the indirect benefit is that you actually see a reduction in the load, or a reduction in the amount of capacity that you need in Dallas to serve all these users. So another indirect benefit, because of there's just much less validity and so much less stuff happening in Dallas, because all these users aren't having to make these trips, and I'm also not having to communicate with users so far away, the Dallas environment may also see an increase in uptime. And then lastly, because the users are not really directly communicating with the servers down in Dallas, you have the indirect benefit of an increase in security through obscurity. So it's pretty basic to understand how a CDN works, in the end, to provide a better benefit to the end user. Thanks for watching this overview of Content Delivery Network. If you liked it or you have any questions, please comment below. Stay tuned for additional videos in the future, and please don't forget to like and subscribe.
Just as the web had became the killer application of the 1990s, email was the killer application of the 1980s. And it remains one of the most important user-facing services on the internet. there are several somewhat independent components in a mail system. One part, the mail transfer agent, has the job of the postman, listening for incoming mail requests from other servers and delivering those messages to a user's inbox, or sending outbound mail from the local system to other remote systems. This part of the protocol is governed by a protocol called Simple Mail Transport Protocol, or SMTP. SMTP is covered most recently by RFC 5321, and we'll take a look at the SMTP protocol in the next slide. Other parts of the mail system work with users to retrieve their mail from their inbox. In days gone by, the mailbox was just a flat file, like a text file, sitting in your home directory, and you could use a command like mail, like that was actually the command, to read that file and show you your inbox and use it to create new messages or delete messages and things like that. More visual versions of mail have emerged in the 1990s. The two most popular were Pine and Elm, but they were still local programs. They ran locally on your machine and nowhere else. Later, we saw the emergence of two network-facing protocols for users to read email on a mail server that wasn't their login server. And that was really a big deal because as email became more popular, the amount of mail that was being delivered increased, and so it quickly became larger than what the small computers of the day could handle. So then you would see a large organization like the university would maintain a separate mail server, but then we needed a way for users to access their mail on that remote mail server. And so POP3 and IMAP were both developed for kind of different purposes. We'll take a look at those shortly. As an example of an application for the network, SMTP is a really nice example. It has a lot in common actually with the HTTP protocol. SMTP is truly a simple mail transfer protocol. It has some well-defined rules. For example, when you first connect to an SMTP server, it's supposed to broadcast itself and say, hello, I am this SMTP server. I support the extended SMTP command. That's what this is trying to say. It even identifies what the software is. So this is the SMTP software called Postfix. That client would then respond with a hello message that says hello and then give it its name. And then the server would respond with a message that said, oh, I can talk to you. Or it would have an error message there that says, no, I can't talk to you. And then the client would respond and the server would respond, and they take their turns. And eventually you get to the point where, for instance, here in this line, what we're doing is we're saying what the data message is going to be. The server says, okay, start typing your data message, and whatever you type in, end it with a blank line followed by a period with a blank line. All right, so this is all going to be the message. This is how you tell SMTP that we're done sending. The SMTP server would then say rejected or queued as some number, and then you quit the SMTP server and everything is closed, and that delivered mail. It's not hard then to understand how we became inundated with what we technically call unsolicited commercial email, or we kind of jargon call spam. SMTP today has evolved. The protocol typically now only accepts messages from trusted hosts. It may require security keys in order to exchange messages with different systems. It may require encryption. There's a bunch of different security things that people have put in place to prevent users from taking advantage of the weaknesses of SMTP. I mean, the simplicity is its strength, but it's also a weakness. So for example, I used to teach a class like this, and we would I would just log on and send email to a student as if they were the President of the United States. And because I was able to compromise the mail system's trust rules, the user got an email from the President of the United States in their inbox. That's much harder to do today because our mail server would look at that and say, wait a second, you can't send email from the whitehouse.gov if you're sitting on a local machine. Like, those two domain names don't match. Old systems didn't do that. So it was a lot of fun. You could really freak people out by sending out messages as like the university president, hey guys, today the school's closed. And it would look really kind of exciting, especially if there was like no snow on the ground. POP3 and IMAP are the two common methods for accessing a remote inbox. The third protocol I don't have listed here would be the Microsoft Exchange protocol. That's one of those closed examples that Microsoft implements just for Outlook and their Microsoft Exchange mail servers. So not as accessible. The documentation is not as accessible. POP3 is the simpler of the two protocols, and it is literally used to move messages from the server to the local machine. And in fact, the idea was that it would retrieve messages from the mail server and then delete them from the mail server to get them off of the shared mail server and local to your computer. And so a client would connect, retrieve messages from the server, delete them as they go, and then when you're done, you disconnect. As new messages arrive on the server, they'll be accumulated, and then the next time the POP client connects, it'll download those messages and delete them. So it's a kind of polling. We're going to essentially keep asking the server, hey, do you have any new messages? And if you don't, then it just disconnects. And if you do, it'll poll them and delete them. Users increasingly wanted to know when they got those messages, like right away. And so they would frequently start decreasing the polling frequency, or increasing the frequency, decreasing the time, sorry. And that's fine if you're connected to, like, you know, a fast system with lots of network capacity, but this can be troublesome on mobile networks. I remember back in the old days when people didn't have unlimited data plans very often. You could actually eat up your data just by setting your mail POP client to check too frequently. IMAP, on the other hand, is a much more advanced. It's a later version of these mail access protocols, and it's much more comprehensive. Like the designers thought about the way that people want to use the mail clients. And instead of just using it as a way of getting your mail off of the server, IMAP is just a way of accessing your mailbox remotely. And so it allows you to do some advanced things like retrieve portions of messages, or even just messages that have changed, or listing directories and folders, moving messages between messages and folders, and things like that. IMAP is a stateful protocol, and so it's going to always remain connected and until you disconnect your device. And because there's that constant connection, the server is able to notify the connected clients and say, hey, a new message just arrived. And so we call that a push. If you were to see these two on the network, you would be able to see the POP start a TCP connection, retrieve whatever messages, and then disconnect, and then 15 minutes later do the same thing. In the IMAP case, you would always see a little bit of like little data squirts going back and forth between the IMAP server and the client, saying, yep, I'm still alive, still here, still waiting, and the server saying, nah, I still got nothing for you. Oh, here's a message for you. And so a little bit more communication, and then when there is data to be exchanged, the two can move data much faster. So just as a thought experiment, imagine if you had to support the hundreds of millions of Gmail users with all of those mobile devices all doing IMAP. It's just hard to imagine how Google's servers can handle that onslaught of users. I mean, it's just kind of, I can't even begin to imagine how some of these services can handle that. So what I thought we could do is go through an example of Packet Tracer and setting up a server and a client and putting them on a network and being able to experiment with getting data back and forth. Okay, what I want to do is go through a simple web server example. We're going to need a PC. That's going to be the web client. We're going to need a server, that is the web server. And we're going to need a little bit of network magic in between to let them connect and talk to one another. So the first thing I'm going to do is I'm going to go down here to this control panel that has all of the different devices that I can use in simulation. And I'm going to pick my endpoint devices. And we're going to grab a PC, and we're going to grab a server. And as they stand right now, they don't talk to one another. They're just kind of hanging out in space. So the simplest way that I could let these two devices talk to one another is on a local area network. And I know we haven't talked about this, so this is new, but if you have a local area network, the device that you would use to connect them is called a switch. So I'm just going to go ahead and grab a Cisco 2960 switch, and we're going to drop that in between them. Now, they're still not connected. I literally have a room full of a PC, a server, and a switch, but that's it. So what I want to do now is wire these things up, and to do that I'm going to add a connection. And I could choose the different connection types, but I'm just going to go ahead and do automatic. And I'm going to connect those two, and we're going to do the same thing. We're going to connect those two. Now, right now it's showing that the switch hasn't recognized the two yet, like they're not connected. That's what this orange dot means. So if I'm just patient for a few seconds, we will see the switch eventually recognize these two guys, and it'll turn green. Okay, so now both of those devices, they can communicate at the Ethernet level, but they can't communicate at the IP address level. Again, we haven't talked about this, but what I need to do is I need to make sure that each one of these two devices has an IP address. So if I was going to do this, I would just click on the server, and there's my picture of my server. And if I go here to desktop, and the first option is IP configuration. And I'm just going to give this guy an IP address of 1.1.1.1. And Cisco will automatically fill in not great subnet mask, but that's fine for right now. And we'll go to our server, or our PC, and we'll do the same thing. I'll go to IP configuration, and we're going to make this one 1.1.1.2. So IP addresses are always integers. They're always 4 digits long, and they're always 8-bit integers. So it's going to be numbers between 0 and 255. So 1.1.1.1 is like the smallest IP address you can have. Again, Cisco will fill in the subnet mask. I can leave everything else kind of the same. So it's always helpful to kind of see, can I actually communicate between these two different machines in command prompt. And what I can do is type in ping 1.1.1.1. That's the PC pinging the server just to say, are you alive? And the server says, I am alive, and I can get there super fast. Okay. So if we can get to the server, let's make sure that the server has our web service turned on. So if I go back to the server, I look at services, and I click on HTTP, I see that HTTP is on. So this is Cisco's way of saying I am a web server. Alright, so go back to the PC, and now what we're going to do is just go here to the web browser, and I'm going to open up HTTP 1.1.1.1, and we'll hit go. And sure enough, I'm connected to the Cisco web server that's built into Packet Tracer.